Welcome to our Yaka Digital Network videos. Every sound you have ever heard, a voice, thunder, footsteps, shares the exact same physical origin. They all begin as a mechanical vibration. Take the adungu, a traditional Ugandan stringed instrument. When a musician plucks the strings, they force the physical material to move rapidly back and forth. That moving string doesn't detach and fly into your ear. Instead, it strikes the air particles immediately surrounding it. Those particles crash into their neighbors, passing the kinetic energy outward in a rapid chain of collisions. Sound is not an object you can capture. It's a strict mechanical event, a continuous transfer of kinetic energy that cannot exist without a source vibration. This transfer of energy moves in a specific geometric pattern, known as a longitudinal mechanical wave. Looking at this 3D slinky model, energy travels from left to right, and individual rings oscillate parallel to its path. Where rings push tightly together are compressions, high atmospheric pressure. Where they spread apart are rarefactions, areas of low pressure. This comparative diagram shows how the physical geometry of these waves dictates what we hear. The top waveform shows a high frequency, with waves packed tightly together, which your ear translates into a high pitch. The bottom waveform displays a taller amplitude. A larger physical displacement of particles transfers more energy, which we perceive as a louder volume. By mapping these alternating regions of pressure and specific heights, we track exactly how a distant disturbance accurately replicates itself inside the human ear. Because sound relies entirely on particles colliding with other particles, it demands a physical medium to propagate. It requires a solid, a liquid, or a gas. This diagram of a bell inside a glass jar proves the rule. When we remove the interior air particles to create a vacuum, the mechanical wave has nothing to travel through. The energy ceases to exist. The speed of that energy depends directly on the density of the medium. This comparative table shows the speed of sound across different states of matter. In solids, where particles are packed tightly together, the kinetic energy transfers almost instantly. Liquids offer a medium speed, while gases, with their loosely scattered particles, carry sound the slowest. This is why a simple string phone works. The taut, solid string transfers the vibration from one cup to the other much faster and more efficiently than the surrounding air. When a moving wave encounters a new object, it can force that object to vibrate at its own natural frequency. We call this resonance. Traditional instrument makers exploit resonance to increase volume. The hollow wooden body of the adungu acts as a resonator. The wood vibrates in sympathy with the strings, physically amplifying the wave's amplitude. The physical environment actively controls the acoustics. The medium dictates if a sound can exist, limits how fast it travels, and determines its final intensity. Let's apply these rules to thermal dynamics. Why does a shout travel at a different speed on a hot afternoon compared to a cold night? Consider a hot, busy street in Gulu. Now contrast that with a misty, cold morning in Kabale. This split-screen diagram visualizes the microscopic difference. On the left, in a hot environment, high temperatures inject kinetic energy into the air. The particles move rapidly and collide with high force, transferring a sound wave swiftly across the space. Looking at the right side, the cold environment lacks that thermal energy. The air particles are sluggish. They cover less distance and collide less frequently, taking visibly longer to pass the same wave from one to the next. Heat acts as a direct multiplier of kinetic energy. Raising the temperature of the environment mathematically increases the velocity of the longitudinal wave. When this wave of moving particles hits a dense obstacle, the energy doesn't just stop. An echo occurs when a sound wave physically reflects off a hard, distant surface, like this steep rock cliff, and travels back to the source. This simple reflection principle scales up into industrial navigation. Ships on Lake Victoria use a technology called sonar to map the invisible depths of the water. This cross-section diagram shows the mechanics of sonar. A ship sends a directed sound pulse downward. The wave hits the solid lake bed and reflects straight back up to a receiver, while a digital timer tracks the entire journey. To convert that time delay into a physical distance, we use a specific mathematical formula. Depth equals speed multiplied by time divided by 2. The division by 2 is the critical step. Because the timer measures the round trip, the wave traveling down and back up, the result must be halved. If the sound takes 4 seconds total, it only took 2 seconds to reach the bottom. Mastering wave reflection takes sound out of the realm of basic communication. It becomes a precise mathematical tool for measuring physical space. The exact same principles applied to a massive lake also work on the microscopic scale within the human body. Ultrasound machines use incredibly high-frequency sound waves, above 20,000 hertz. Because their wavelengths are so short, they safely reflect off soft internal tissues rather than rock. Doctors at facilities like St. Joseph's Hospital use these echoes to generate real-time medical imagery. Let's review the core rules on this summary board. We have established that all sound is a mechanical vibration, generating a longitudinal wave of compressions and rarefactions. This transfer of energy absolutely requires a physical medium, and its speed is strictly governed by the density and temperature of those particles. Finally, we can use the wave's reflection to calculate distance through the echo formula. Distance equals velocity times time divided by 2. Sound is a mechanical interaction between energy and matter. It is governed by strict, observable physical laws that allow us to calculate, map, and understand our world. You can watch more videos for all classes here and get all content at www.yaka.cc.